Tonight, we journey into the crystalline world of ice, a substance so familiar yet so extraordinary in its nature and behavior. Ice shapes our planet's climate, sculpts landscapes across millennia, and exists throughout our solar system in forms both delicate and vast. Just before we begin, if these calm, curious explorations help you unwind or give you a quiet way to end your day, please consider liking and subscribing to the channel. It helps others find their way here too. As you settle into comfort, let your mind drift through these gentle revelations about frozen water, each fact a soft stepping stone into deeper rest, each truth a whisper from winter's realm, inviting you toward peaceful sleep. Ice is less dense than liquid water, a remarkable property that makes ice float, an anomaly among substances that typically become denser when they solidify, sinking into their liquid forms rather than rising above them. This unusual behavior occurs because water molecules arrange themselves into an open hexagonal lattice when freezing, creating more space between molecules than exists in liquid water's more chaotic arrangement. If ice behaved like most substances and sank when frozen, Earth's oceans would freeze from the bottom up, trapping frigid water beneath and fundamentally altering marine ecosystems, perhaps making complex life impossible. Instead, floating ice insulates the water below, allowing aquatic life to survive winter's coldest temperatures in the liquid refuge beneath protective ice layers, a quirk of chemistry that may have enabled life's evolution on our planet. Water expands by approximately 9% when it freezes into ice, a powerful transformation that can burst pipes, crack rocks, and reshape landscapes through the inexorable force of crystallization. This expansion explains why frozen water bottles bulge and sometimes rupture, why canned beverages left in freezers explode into frozen shrapnel, and why homeowners fear winter's deep cold reaching their plumbing. The force generated by freezing water is extraordinary, exerting pressures exceeding 25,000 pounds per square inch in confined spaces, strong enough to split solid rock and capable of gradually fragmenting entire mountain ranges through countless freeze-thaw cycles over geological time. This relentless expansion has carved landscapes for millennia, widening cracks into fissures, breaking apart boulders, creating the fractured terrain we observe in cold regions where water's phase change serves as a patient but powerful sculptor. Ice forms a crystalline hexagonal structure at the molecular level, each water molecule bonding with four neighbors in a tetrahedral arrangement that extends into a repeating six-sided pattern throughout the crystal. This hexagonal architecture isn't random, but rather represents the most stable configuration for water molecules connected by hydrogen bonds at temperatures below freezing, minimizing energy while maximizing structural stability. The six-fold symmetry appears at every scale, from individual molecular arrangements invisible to the naked eye to the macroscopic six-pointed stars of snowflakes visible on your winter coat. This consistent geometry across scales demonstrates how molecular forces dictate large-scale structure, how the invisible architecture of atoms and bonds manifests in the visible world, creating the distinctive patterns we recognize as characteristically frozen. The hydrogen bonds in ice create its characteristic six-sided symmetry, these relatively weak attractions between molecules organizing water into geometric perfection as thermal motion decreases and molecular order increases. Hydrogen bonds form when water's slightly positive hydrogen atoms attract neighboring molecules' slightly negative oxygen atoms, creating a network of connections that locks molecules into fixed positions at freezing temperatures. Each water molecule can form four hydrogen bonds simultaneously, creating a three-dimensional lattice where the angle between bonds naturally produces hexagonal symmetry, like building a structure where every joint bends at precisely the same angle. This bonding pattern explains not just ice's structure but also many of water's unusual properties, from its high boiling point to its excellent solvent capabilities, making hydrogen bonding one of nature's most consequential intermolecular forces. Ice appears transparent because its crystal structure is highly ordered, allowing light to pass through without scattering significantly, unlike snow which appears white due to its jumbled crystal orientations that scatter light in all directions. In perfectly formed ice crystals, molecules arrange themselves in regular, repeating patterns with minimal defects or irregularities to deflect passing photons, permitting light to traverse the material relatively unimpeded. This transparency allows sunlight to penetrate frozen lakes and rivers, reaching aquatic plants and organisms living beneath the ice, maintaining photosynthesis during winter months when surface ice would otherwise block all light. The clarity of ice varies with its formation conditions. Ice frozen slowly creates larger, more perfect crystals with fewer internal boundaries and greater transparency, while rapidly frozen ice traps air bubbles and impurities that scatter light, creating the cloudy appearance common in freezer ice cubes. Pure ice is colorless but can appear blue due to light absorption, with thick ice absorbing red wavelengths preferentially while allowing blue light to travel further through the frozen structure before emerging. This selective absorption occurs because water molecules, even in solid form, absorb light more readily at the red end of the spectrum, removing warm colors from light passing through while permitting cooler wavelengths to continue their journey. The effect becomes noticeable only in thick ice masses like glaciers, where light travels meters through ice before reaching your eyes, accumulating enough red light absorption to shift the remaining light toward the blue end of the spectrum. This phenomenon explains why glacial ice appears so intensely blue in crevasses and caves where sunlight penetrates deep into ancient compressed ice, the same physics that makes the ocean appear blue but operating in frozen form. Ice has a density of about 0.92 grams per cubic centimeter, approximately 8% less dense than liquid water's 1 gram per cubic centimeter. This difference explaining why ice floats with roughly 90% of its volume submerged beneath the surface. This specific density relationship determines how icebergs float, why ice cubes protrude slightly above your drink's surface, and how thick ice must grow before it can support a person's weight safely. The exact density varies slightly depending on ice's temperature and crystalline form, with colder ice being marginally denser than warmer ice near the melting point, though all common forms of ice remain less dense than liquid water. This consistent density difference creates predictable floating behavior that has influenced everything from Arctic exploration to the design of ships navigating ice-filled waters, where understanding ice's buoyancy becomes essential for safety. Fresh water freezes at 0 degrees Celsius, 32 degrees Fahrenheit, at standard atmospheric pressure. This precise temperature marking the boundary where liquid water's thermal energy equals the bonding energy required to lock molecules into crystalline structure. At this critical temperature, water molecules move slowly enough that hydrogen bonds can capture them into fixed positions within the growing crystal lattice, though the actual freezing process often requires supercooling slightly below zero or the presence of nucleation sites where ice crystals can begin forming. Pure water in pristine containers can supercool several degrees below freezing without solidifying, remaining liquid until disturbed. But water in nature typically contains enough impurities and irregularities to begin freezing at or very near the standard freezing point. This reliable transition temperature has served humanity as a calibration point for thermometers and temperature scales for centuries, a reproducible natural phenomenon anchoring our measurement of thermal energy. Salt water freezes at lower temperatures than fresh water, around -2 degrees Celsius or 28 degrees Fahrenheit for typical ocean salinity, because dissolved salt ions interfere with water molecules' ability to bond into the organized crystal structure that characterizes ice. The salt ions insert themselves between water molecules, disrupting the hydrogen bonding network required for crystallization, forcing temperatures lower before thermal motion decreases enough for ice to form despite this interference. This freezing point depression becomes more pronounced as salinity increases, with the Dead Sea's extremely salty water remaining liquid at temperatures well below zero, while slightly brackish water freezes only a degree or so below the freshwater freezing point. This property has profound implications for polar oceans, where sea ice formation excludes salt from the growing crystals, creating pockets of extra salty brine that sink through the water column, driving ocean circulation patterns that distribute heat globally. Ice can exist in at least 18 different crystalline forms depending on pressure and temperature, each polymorph exhibiting distinct molecular arrangements and physical properties, though most exist only under extreme conditions never encountered in everyday experience. These exotic ice forms emerge under the tremendous pressures found deep within ice-covered moons, beneath massive glaciers, or in laboratory diamond anvil cells that recreate otherworldly conditions on Earth. Some high-pressure ice forms are denser than water and sink, reversing the familiar floating behavior of ordinary ice, while others exhibit unusual properties like remaining solid at room temperature as long as crushing pressure is maintained. These diverse crystalline structures reveal water's remarkable versatility, its molecules capable of organizing into dramatically different configurations depending on environmental conditions, each form representing a different solution to the problem of packing water molecules efficiently under specific pressure and temperature constraints. The most common form of ice on Earth is called ice IH, the H designating hexagonal to distinguish it from the cubic ice variant that occasionally forms under specific conditions, though hexagonal ice dominates overwhelmingly in natural settings. This particular polymorph forms at atmospheric pressure and temperatures below 0 Celsius, creating the ice that forms in your freezer, blankets, winter lakes, and comprises glaciers and polar ice caps. Ice IH's hexagonal structure dictates the six-fold symmetry observed in snowflakes, frost patterns, and ice crystals throughout nature, making this specific molecular arrangement responsible for winter's characteristic geometric beauty. Every ice cube you've encountered, every snowflake that's landed on your sleeve, every frozen puddle you've stepped across represents Ice I, the dominant form of frozen water in Earth's accessible environment, so common that we simply call it ice without qualification. Under extreme pressure, ice becomes denser than water and sinks, a reversal of normal behavior that occurs when pressure forces water molecules into more compact arrangements than possible at atmospheric conditions, creating high-pressure ice polymorphs with properties alien to everyday experience. This transformation occurs at pressures exceeding about 200 megapascals, roughly 2,000 times atmospheric pressure, found deep beneath massive ice sheets or created in laboratory pressure vessels that subject ice to forces equivalent to being crushed beneath hundreds of kilometers of rock. These dense ice forms occupy less volume than the water they formed from, contradicting the familiar expansion that occurs during normal freezing, and some remain stable at room temperature as long as pressure is maintained. This behavior suggests that deep beneath the ice shells of ocean worlds like Europa or Enceladus, exotic high-pressure ice forms might exist, denser than the liquid oceans they overlie, creating layered structures unlike anything found on Earth. Ice 7 exists at pressures above 3 gigapascals and remains solid even at room temperature, maintaining its crystalline structure despite thermal energy that would vaporize normal ice, held together by the crushing force of extreme pressure. This exotic form features a curious structure where two interpenetrating ice lattices coexist, molecules from one lattice passing through spaces in the other without bonding between them, creating a configuration impossible under normal pressure conditions. Ice 7 forms in shock experiments where massive impacts or explosions briefly create enormous pressures, and scientists speculate it might exist within diamond inclusions, trapped when diamonds formed deep in Earth's mantle where extreme pressure could stabilize this unusual phase. Remarkably, Ice 7 was recently discovered as natural inclusions within diamonds, marking the first confirmed observation of this high-pressure ice polymorph in nature, frozen in time and pressure within crystalline prisons that preserve exotic ice from Earth's deep interior. Ice 11 is a ferroelectric form that exists at very low temperatures, where water molecules align their electric dipoles in the same direction throughout the crystal, creating ice with a permanent electric polarization, a phase predicted theoretically but difficult to create experimentally. This exotic form appears when ice IH is cooled below about -200 degrees Celsius while simultaneously treated with traces of potassium hydroxide that help molecules rotate into their aligned configuration, overcoming the energy barriers that normally prevent this ordering. The ferroelectric properties mean Ice 11 responds to electric fields differently than ordinary ice, potentially relevant for understanding the electrical properties of ice on outer solar system bodies, where temperatures reach the extreme cold required for this phase transition. However, Ice 11 remains challenging to create and study, existing only in specialized laboratory conditions, representing the kind of obscure ice polymorph that reveals water's complexity while having negligible practical impact on the frozen water we encounter daily. Amorphous ice lacks crystalline structure and forms at extremely low temperatures or through rapid cooling that prevents molecules from organizing into regular geometric patterns, creating a frozen state that resembles glass more than conventional ice. This disordered solid forms when water vapor condenses onto surfaces colder than about -160 degrees Celsius, or when liquid water cools so rapidly that molecules freeze in place before they can arrange into crystals, preserving the random molecular positions characteristic of the liquid state. Amorphous ice exists in two distinct forms, low density and high density, depending on formation conditions, and transitions between these forms might occur in comets and icy moons when temperature or pressure changes. Some scientists believe amorphous ice dominates in interstellar space, coating dust grains in molecular clouds, making this glassy form of frozen water potentially more abundant in the universe than crystalline ice, though nearly absent from Earth where temperatures and pressures favor crystalline forms. About 10% of Earth's land surface is covered by glacial ice, approximately 15 million square kilometers blanketed in frozen water that flows imperceptibly downhill under its own immense weight, reshaping landscapes through gradual but relentless motion. This ice exists primarily in Earth's polar regions, Antarctica, Greenland, and the Arctic archipelagos, where temperatures remain cold enough year-round to preserve accumulated snow that gradually compresses into glacial ice. Mountain glaciers contribute additional ice cover at high elevations, even in tropical latitudes, where altitude compensates for warmth, allowing permanent ice to persist on peaks like Kilimanjaro despite equatorial location. This 10% figure, while seemingly small, represents an enormous mass of frozen water containing most of Earth's accessible fresh water, and fluctuations in this ice coverage have driven sea level changes throughout history, alternately exposing and flooding coastal regions as ice ages came and went, reshaping human geography and migration patterns. Antarctica contains about 90% of Earth's ice, this frozen continent holding such vast quantities that its ice sheets, if melted, would dramatically reshape global geography and climate beyond recognition. The Antarctic ice sheet averages about 2 kilometers thick, reaching nearly 5 kilometers at its deepest point, a mass of ice so heavy it actually depresses the bedrock beneath, pushing continental crust down into the mantle under the tremendous weight of frozen water. This single ice sheet contains more ice than all other glaciers, ice sheets, sea ice, and permafrost on Earth combined, making Antarctica the planet's dominant reservoir of frozen freshwater by an overwhelming margin. The ice has accumulated over millions of years, each winter's snowfall compressed by subsequent layers into an archive of ancient atmosphere and climate, preserving information about Earth's past in chronological layers extending back nearly 1 million years into history recorded in ice. The Antarctic ice sheet holds approximately 26.5 million cubic kilometers of ice, a volume so immense it challenges comprehension, containing enough frozen water to cover the entire United States in ice over 3 kilometers deep. This mass represents roughly 70% of Earth's fresh water, locked in solid form far from human population centers, inaccessible for consumption yet profoundly influencing global climate, ocean circulation, and sea level. The ice sheet's enormous volume reflects millions of years of accumulated snowfall, each year's precipitation adding another thin layer that gradually compresses under its own weight, transforming from fluffy snow to dense glacial ice over centuries and millennia. Scientists monitor this vast reservoir carefully, for even small fractional changes in its volume would significantly affect coastal communities worldwide, making Antarctic ice a crucial variable in understanding future climate and civilization's relationship with a changing planet. If all Antarctic ice melted, global sea levels would rise about 58 meters, approximately 190 feet, enough to submerge most coastal cities and fundamentally redraw world maps, transforming geography and displacing billions of people from low-lying regions. This scenario would flood major metropolitan areas like New York, London, Shanghai, and Mumbai, push coastlines dozens or hundreds of kilometers inland on flat terrain, and eliminate entire island nations, creating a geography where mountain peaks become islands and former highlands become the new coastline. Such melting would require warming far beyond current projections, taking thousands of years even under extreme climate scenarios, but the potential for this transformation demonstrates the immense volume of water currently stored as Antarctic ice. This hypothetical scenario serves as a stark illustration of ice sheet's importance in regulating sea level, showing how frozen water's location, on land versus in ocean, determines whether it contributes to sea level rise when melting occurs. Greenland's ice sheet contains enough ice to raise sea levels by about 7 meters, A substantial contribution, though smaller than Antarctica's potential impact, still sufficient to flood coastal regions and major cities if completely melted over centuries or millennia. This ice sheet covers about 1.7 million square kilometers, nearly the entire island except for narrow coastal margins, with ice averaging over 2 kilometers thick and reaching over 3 kilometers at its thickest point. Unlike Antarctica's extremely cold and relatively stable ice sheet, Greenland's lower latitude exposes it to warmer temperatures and more active melting, making it particularly vulnerable to climate change and responsible for measurable contributions to current sea level rise. Scientists monitor Greenland's ice loss carefully through satellite measurements, observing acceleration in both surface melting and outlet glacier flow, changes that provide real-time evidence of climate warming's effects on major ice sheets and preview larger transformations that might unfold over coming centuries. Glaciers store about 69% of the world's fresh water, making ice Earth's dominant freshwater reservoir by far, dwarfing the water held in lakes, rivers, swamps, and shallow groundwater combined by more than 2 to 1. This frozen storage system contains water that fell as precipitation decades, centuries, or millennia ago, captured and preserved in solid form until eventual melting releases it to rivers and oceans. The concentration of freshwater in glaciers means that seasonal and long-term ice changes directly affect water availability for billions of people who depend on glacier-fed rivers for drinking water, irrigation, and hydroelectric power, particularly in Asia, where major rivers like the Ganges, Indus, and Yangtze receive significant glacial meltwater. This dependence creates vulnerability as glaciers worldwide retreat, potentially reducing summer river flows when agricultural demand peaks, threatening water security in regions where glacial meltwater supplements rainfall-fed river flow during dry seasons. The oldest continuous ice core samples recovered extend back about 800,000 years, though surface blue ice samples have been dated to 2.7 million years old, providing direct windows into Earth's atmospheric history across multiple glacial cycles. These cores, drilled from Antarctica's thick ice sheets, preserve annual layers of accumulated snow compressed into ice, each layer containing tiny air bubbles that trapped atmospheric gases at the time of formation. By analyzing these bubbles, scientists directly measure past atmospheric carbon dioxide, methane, and other gases, while isotopic analysis of the ice itself reveals temperature variations, creating a detailed climate record spanning nearly 1 million years. This archive shows Earth's climate oscillating through regular ice age cycles, with carbon dioxide levels rising and falling in lockstep with temperature, providing crucial evidence for understanding climate's sensitivity to greenhouse gases and offering context for evaluating modern atmospheric changes against the range of natural variability recorded in ancient ice. Ice cores preserve ancient atmospheric gases in tiny air bubbles, trapping samples of past atmosphere between ice crystals as snow compresses into solid ice, creating a chronological record of air composition extending back hundreds of thousands of years. These microscopic time capsules form when snow accumulates faster than air can escape, gradually compressing into firn, partially compacted snow, and eventually solid ice, sealing air pockets between crystals that preserve atmospheric composition from the time of snow formation. Scientists extract these bubbles by crushing or melting ice samples in vacuum chambers, analyzing the released gases with extraordinary precision to determine past concentrations of carbon dioxide, methane, nitrous oxide, and other atmospherically important compounds. This technique provides the only direct measurements of ancient atmosphere, complementing indirect proxy methods and enabling scientists to correlate greenhouse gas concentrations with temperature changes throughout Earth's climate history, demonstrating the tight coupling between atmospheric composition and global temperature across hundreds of millennia. Scientists can determine past temperatures by analyzing oxygen isotopes in ice cores, measuring the ratio of heavy oxygen 18 to normal oxygen 16 in water molecules, which varies predictably with the temperature at which snow formed. Warmer temperatures during snow formation result in relatively more heavy oxygen incorporated into snowflakes because the lighter isotope evaporates more readily and condenses less readily than heavy oxygen, creating temperature-dependent fractionation. By measuring these isotope ratios in sequential ice layers, researchers reconstruct temperature histories with remarkable precision, revealing not just ice age cycles, but also shorter-term climate fluctuations like the abrupt warmings and coolings that punctuated the last glacial period. This isotopic thermometer works because the physical laws governing evaporation and condensation discriminate between isotopes in predictable ways, allowing ice to preserve temperature information in its molecular composition, creating a frozen archive readable by those who understand water's isotopic language. The Cuelcaya ice cap in Peru contains the world's largest tropical ice mass, sitting at 5,470 meters elevation, where altitude creates temperatures cold enough to maintain permanent ice despite tropical latitude. This ice cap demonstrates how elevation can overcome latitude's warming influence, creating glacial conditions mere degrees from the equator, where temperature decreases about 6.5 degrees Celsius per kilometer of altitude gained. Cuelcaya's ice has retreated dramatically in recent decades, with its margins receding at rates exceeding 60 meters per year in some locations, revealing plants that grew thousands of years ago before ice advanced over them. This tropical glacier serves as a sensitive climate indicator, responding more rapidly to temperature changes than polar ice because it exists near the threshold between frozen and melted states, where small temperature shifts dramatically affect ice accumulation and melting rates, making tropical glaciers early warning systems for climate change. Permafrost, permanently frozen ground, covers about 24% of land in the northern hemisphere, underlying vast stretches of Alaska, Canada, Siberia, and other high-latitude regions where soil remains frozen year-round despite summer surface thaw. This frozen soil extends from just below the surface to depths exceeding 1,500 meters in some locations, persisting from Ice Age times when colder temperatures froze ground that hasn't yet thawed completely despite subsequent warming. Permafrost contains enormous quantities of organic matter, dead plants and animals frozen before decomposition could release their carbon, creating a vast reservoir of potentially greenhouse gases that could accelerate climate warming if released through thawing. Recent observations show permafrost temperatures rising and thaw depth increasing, initiating a feedback loop where warming thaws frozen soil, releasing methane and carbon dioxide that cause additional warming, which thaws more permafrost, creating a self-reinforcing cycle that could significantly amplify human-caused climate change over coming decades and centuries. Sea ice covers approximately 7% of Earth's ocean surface, floating on polar seas where frigid temperatures freeze the top layer of ocean water into vast expanses of ice that expand in winter and contract in summer in annual cycles. Unlike glaciers and ice sheets that form on land from accumulated snowfall, sea ice grows directly from freezing seawater, creating a distinct form of ice that contains salt-rich brine pockets between ice crystals and floats at the ocean surface. This floating ice doesn't contribute to sea level rise when it melts because it already displaces its weight in water while floating, but its presence profoundly affects regional climate by reflecting sunlight, insulating ocean from atmosphere, and providing habitat for specialized species adapted to icy marine environments. Sea ice serves as a sensitive climate indicator, responding quickly to temperature changes, and Arctic sea ice has declined dramatically in recent decades, losing roughly half its summer extent compared to 1980s observations, revealing dark ocean water that absorbs sunlight and accelerates regional warming. Arctic sea ice reaches maximum extent in March and minimum in September, following annual cycles where winter's cold grows ice outward from the polar center while summer's warmth melts it back toward a smaller core of persistent ice. This seasonal oscillation typically ranges from about 15 million square kilometers at maximum to about 5 million at minimum, a threefold variation representing an area of ice larger than the United States appearing and disappearing annually. The timing reflects northern hemisphere seasons, with maximum ice following months of winter darkness and cold, while minimum ice occurs after months of continuous sunlight and warming, though ice extent lags behind temperature extremes because melting and freezing require time to transfer heat through ice thickness. Recent decades have seen both maximum and minimum extents declining, with summer minimum ice declining particularly rapidly, shrinking at about 13% per decade and approaching half its 1980s extent, a transformation visible to satellite observations tracking Arctic ice continuously since 1979. Multi-year sea ice can be several meters thick, surviving multiple summer melt seasons to grow progressively thicker as each winter adds new ice to the surviving core, creating much more robust ice than the thin first-year ice that barely survives its first summer. This older ice develops distinctive characteristics. smoother surface as repeated melting, freezing cycles, smooth irregularities, lower salinity as brine gradually drains from aging ice, and greater structural strength as crystal structure anneals over time. Multi-year ice once dominated the Arctic Ocean's central regions, but recent warming has dramatically reduced its extent and thickness, with first-year ice now comprising much larger portions of Arctic sea ice than in previous decades. This transition weakens overall ice coverage because thin first-year ice melts far more readily than thick multi-year ice, creating a feedback where thinning ice melts more easily, reducing the amount that survives summer to become thicker multi-year ice, further increasing the proportion of thin ice vulnerable to future melting. Lake Baikal in Siberia freezes with ice so clear you can see 40 meters deep, creating surreal winter landscapes where people appear to float above underwater terrain visible through transparent ice. This extraordinary clarity arises from Baikal's exceptional water purity combined with rapid freezing that creates large defect-free ice crystals with minimal trapped air bubbles or impurities to scatter light. The lake's ice reaches over a meter thick by winter's end, strong enough to support trucks crossing its frozen surface, yet remains transparent enough to observe fish swimming beneath and see bottom features in shallow areas. This crystalline ice creates unique formations, vertical cracks that form as temperature fluctuations cause ice to contract and expand, creating pressure ridges where ice blocks thrust upward and turquoise ice shards that pile up along shorelines like scattered glass, all illuminated by sunlight streaming through ice to the depths below. Glaciers form when accumulated snow compresses into dense ice over many years, this transformation occurring as each winter's snowfall survives summer melting and is gradually buried by subsequent snowfall, creating conditions where snow compacts under its own increasing weight. Fresh snow's fluffy structure, filled with air spaces between delicate crystals, slowly collapses as pressure from overlying snow forces crystals to pack more tightly together, first becoming granular snow called firn with density intermediate between snow and ice. Over decades or centuries, depending on accumulation rate and temperature, continued pressure squeezes out remaining air pockets and fuses grains together, transforming firn into glacial ice with distinctive blue color and densities approaching pure ice's theoretical maximum. This process requires specific climate conditions where winter snowfall exceeds summer melting over sustained periods, allowing accumulation to build the necessary thickness for compression to drive the snow-to-ice transformation that creates glaciers. Glacial ice can be hundreds of thousands of years old, particularly in Antarctica's central ice sheet where extremely cold temperatures and minimal melting allow ice to accumulate and persist across vast time spans, creating frozen archives extending back nearly 1 million years. This ancient ice began as snowfall during previous ice ages, gradually buried by subsequent accumulation and compressed into solid ice that flows slowly toward glacier margins where it eventually melts or carves into the ocean. The age of ice increases with depth in ice sheets, with surface ice recently formed and bottom ice potentially hundreds of thousands of years old, though the age-depth relationship becomes complex where ice flows over irregular bedrock or where melting at the base removes the oldest ice. Dating ice cores involves counting annual layers visible in chemical composition or physical properties, supplemented by various isotopic dating techniques for ice too old to show distinct annual layers, revealing the remarkable longevity of ice in places cold enough to preserve frozen water across timescales comparable to human evolution. Glaciers flow downhill due to gravity and the weight of accumulated ice, moving despite being solid because ice, like extremely stiff honey, can deform and flow under sustained pressure even at temperatures well below its melting point. This flow occurs through two main mechanisms: internal deformation, where ice crystals slowly slide past each other under stress, and basal sliding, where the glacier's bottom slides over bedrock lubricated by meltwater from pressure melting or geothermal heat. Flow rates vary dramatically depending on ice thickness, slope, and temperature, ranging from centimeters per year for cold, thin glaciers to meters per day for large, steep glaciers with water-lubricated bases. This slow but inexorable motion makes glaciers powerful geological agents, carrying embedded rocks that scour bedrock, carving distinctive U-shaped valleys, and transporting eroded material vast distances from source to eventual deposition, reshaping landscapes through patient but relentless frozen flow. The fastest moving glacier is Jakobshavn Glacier in Greenland, moving about 40 meters per day at its fastest recorded speed, draining a substantial portion of Greenland's ice sheet and carving enormous icebergs into Disco Bay. This remarkable velocity occurs where the glacier reaches the sea, floating on ocean water while still connected to inland ice, creating conditions that reduce basal friction and allow rapid flow driven by the ice sheet's tremendous weight pushing from behind. Jakobshavn has accelerated dramatically in recent decades as warming ocean water melted its floating ice tongue, removing the buttressing effect that previously slowed flow, demonstrating how marine terminating glaciers can respond quickly to ocean temperature changes. This glacier produces roughly 10% of all icebergs from Greenland, despite representing only a small fraction of the ice sheet, including the iceberg that likely sank the Titanic, making it both scientifically important as an indicator of ice sheet change and practically significant as a major iceberg source. Glaciers carve valleys through erosion, creating U-shaped valleys with characteristic steep sides and flat floors that distinguish glacially carved terrain from the V-shaped valleys created by river erosion. This distinctive shape arises because glaciers erode across their entire width rather than concentrating erosion in a narrow channel like rivers, plucking rock fragments from valley walls and floor, transporting embedded rocks that scour bedrock like slow-motion sandpaper, gradually widening and deepening valleys into characteristic profiles. The erosive power depends on ice thickness, flow velocity, and the abundance of rock debris embedded in basal ice that acts as cutting tools. Thick, fast-moving glaciers with debris-rich bases carve most effectively, excavating deep troughs over thousands of years. Post-glacial U-shaped valleys often contain lakes where bedrock depressions excavated by ice filled with water after glaciers retreated, and they exhibit characteristic features like hanging valleys where tributary glaciers entered at elevations high above the main valley floor, creating dramatic waterfalls where streams plunge from hanging valleys to valley floors far below. Glacial ice appears blue because it absorbs red light wavelengths, this selective absorption becoming noticeable in thick, dense ice where light travels sufficient distance for red light's preferential absorption to significantly shift transmitted light toward blue wavelengths. The phenomenon requires ice thick and pure enough for light to penetrate deeply, explaining why small ice cubes appear clear while glacial crevasses glow intense blue, and why compressed glacial ice shows stronger blue coloration than bubbly, light-scattering ice near glacier surfaces. The blue intensity depends on ice thickness and purity. The clearest, densest ice exhibits the most vivid blue because light travels farthest without being scattered by bubbles or impurities, accumulating more red light absorption before emerging as predominantly blue light. This coloration creates stunning visual effects in glacial ice caves and crevasses, where concentrated blue light produces an otherworldly glow, nature's light filtering creating a color distinctive to thick, ancient ice compressed over centuries into bubble-free clarity. Crevasses in glaciers can be over 30 meters deep, these dramatic cracks forming where glaciers flow over irregular terrain or accelerate, creating stresses that exceed ice's ability to deform smoothly, causing brittle fracture instead. Crevasses open perpendicular to the direction of maximum tension, creating distinctive patterns that reveal stress distribution within flowing ice. Transverse crevasses where ice accelerates, longitudinal crevasses where ice spreads laterally, and splaying crevasse patterns where ice flows around obstacles. These gaps pose serious hazards to glacier travelers, particularly when hidden beneath snow bridges that camouflage deep voids invisible from the surface until someone steps through the fragile snow covering, plunging into the hidden depths below. Crevasse depth is limited by the depth at which ice becomes warm and ductile enough to deform rather than fracture, typically 30 to 40 meters in temperate glaciers where pressure and geothermal heat soften deeper ice, explaining why crevasses rarely extend to glacier beds despite dramatic surface appearance. Glaciers contain about 3 times more water than all the world's rivers and lakes combined, this comparison highlighting the vast volume of fresh water stored in solid form despite ice covering only 10% of land surface. The disparity arises because glaciers average hundreds of meters thick, while lakes rarely exceed a few hundred meters depth and cover much smaller areas, and rivers contain only the tiny fraction of water currently in transit from high elevations to oceans. This frozen storage significantly exceeds readily accessible liquid freshwater, meaning that while glaciers technically contain freshwater, they don't provide easy access compared to rivers and lakes that flow conveniently near human settlements. Glaciers serve instead as long-term water storage, buffering climate variations by accumulating water during cold, wet periods and releasing it during warm, dry periods, providing meltwater that sustains river flow long after rainfall ceases, particularly crucial for communities downstream from mountains where glaciers act as natural water towers. During the last ice age, ice sheets covered approximately 30% of Earth's land surface, vastly more extensive than today's 10% ice coverage, with massive ice sheets extending far into regions that are now temperate landscapes. These continental ice sheets covered Canada, northern United States, northern Europe and northern Asia, with ice over 3 kilometers thick at their centers, so massive that their weight depressed Earth's crust hundreds of meters into the mantle. Depressions still rebounding upward today, thousands of years after ice retreated. The expanded ice coverage locked up so much water that global sea level dropped about 120 meters below present levels, exposing vast continental shelves as dry land connecting islands to continents and allowing human and animal migrations across now submerged land bridges. This Ice Age configuration, which prevailed as recently as 20,000 years ago, demonstrates ice's enormous potential influence on Earth's geography, climate, and habitability, showing how relatively modest global cooling can trigger massive ice expansion that fundamentally reorganizes landscapes. The Hubbard Glacier in Alaska is advancing while most glaciers retreat, moving forward and adding ice to its terminus even as global temperatures rise and glaciers worldwide shrink, demonstrating that individual glacier behavior can diverge from global trends due to local conditions. This advance occurs because Hubbard receives exceptional snowfall in its accumulation zone at high elevations where precipitation remains frozen, and this snow input exceeds melting at the glacier's terminus, allowing net ice gain despite regional warming. The glacier has surged forward dramatically at times, advancing rapidly enough to block Russell Fjord from the ocean, temporarily converting a saltwater fjord into a freshwater lake until the ice dam failed and ocean water rushed back in. This behavior illustrates how glacier dynamics depend on local factors, snowfall, temperature, bedrock geometry, and ice physics, that can temporarily overwhelm broader climate trends, though most glaciers respond to warming by shrinking as melting outpaces snowfall accumulation. Only about 10 to 15% of an iceberg's mass is visible above water, the overwhelming majority remaining hidden beneath the surface due to ice's near-neutral buoyancy in seawater, floating with approximately 90% submerged and 10% exposed. This proportion arises from ice's density of about 0.92 grams per cubic centimetre compared to seawater's 1.025 grams per cubic centimetre, meaning ice floats with a buoyancy similar to wood in freshwater, creating hazardous conditions where an iceberg's visible portion poorly indicates the massive obstacle lurking below. The exact proportion varies with ice density, which depends on trapped air bubbles and ice temperature, and with water salinity, which affects seawater density, but the roughly 9:1 ratio of submerged to exposed ice remains consistent enough to make tip of the iceberg a meaningful metaphor for situations where visible portions hint at much larger hidden dimensions. This hidden mass makes icebergs hazardous to ships, which can collide with submerged ice while maintaining what appears to be safe distance from the visible portions, creating dangers that persist despite radar and satellite monitoring. The largest iceberg ever recorded was larger than Jamaica, covering 11,000 square kilometers when it calved from Antarctica's Ross Ice Shelf in 2000, a mass so enormous it remained identifiable on satellite images for years as it drifted through the Southern Ocean. This giant, designated B-15, eventually fragmented into smaller pieces through wave action, thermal stress, and collisions with ocean floor features, but some fragments survived for over a decade before finally melting completely. Such enormous icebergs form only from ice shelves, thick floating ice attached to land ice, where large tabular sections can break off in single calving events, unlike smaller icebergs from tidewater glaciers that calve more frequently but in smaller pieces. These giant bergs can profoundly affect local ocean conditions, blocking ocean currents, trapping sea ice, and creating sheltered zones behind them where ocean circulation changes, demonstrating how even temporary ice features can influence regional oceanography until they drift away or disintegrate. Icebergs can be several hundred meters thick, particularly tabular icebergs from Antarctic ice shelves that carve as flat-topped slabs with thickness matching the ice shelf's original dimensions, sometimes exceeding 300 meters from waterline to bottom. This thickness makes them extremely massive despite often being relatively short in horizontal dimensions, with some icebergs containing more ice in their compact thickness than in their visible surface area might suggest. The thickness determines how deeply icebergs penetrate the water column, with the deepest icebergs extending hundreds of meters below the surface, where they can scrape across seafloor features in shallow waters, ploughing through sediments and disturbing benthic ecosystems. This deep draft also exposes icebergs to deeper ocean currents that may flow in different directions than surface currents, causing complex iceberg trajectories as different water masses at different depths push and pull the berg in competing directions, making iceberg drift patterns difficult to predict despite sophisticated ocean modeling. Icebergs carve or break off from glaciers and ice shelves, this dramatic process occurring when ice flowing toward the sea extends beyond its support and breaks under its own weight, or when ocean waves and tides flex floating ice until cracks propagate and chunks separate. Calving rates depend on many factors, including glacier velocity, ice thickness, water depth, and ocean temperature, with warmer water increasing calving by melting ice from below and creating instability. The process can be sudden and violent, with massive ice blocks crashing into the ocean and generating waves dangerous to nearby boats, though most calving occurs continuously through smaller events as ice gradually fractures rather than catastrophic failures. Calving represents the primary way glaciers lose mass in regions where they reach the sea, balancing the ice flow from inland accumulation zones. If calving exceeds ice supply, glaciers shrink and retreat, while if ice supply exceeds calving, glaciers advance, making calving rates crucial for determining glacier behavior and contributions to sea level. Antarctic icebergs are typically tabular, with flat tops, while Arctic ones are more irregular, this difference reflecting the distinct ice sources and carving processes in each polar region. Antarctic icebergs carve primarily from vast floating ice shelves that spread across the ocean surface like frozen sheets, breaking off as geometric slabs that maintain the ice shelf's flat upper surface, creating tabular bergs with vertical sides and horizontal tops like floating ice tables. Arctic icebergs come mainly from Greenland's tidewater glaciers that end at the sea as steep ice cliffs, carving as irregular chunks that tumble and rotate when entering the water, emerging in diverse shapes including spires, domes, and jagged blocks. These shapes affect drift patterns and longevity, with tabular icebergs' large surface area making them vulnerable to surface melting, but their compact geometry providing stability, while irregular icebergs' complex shapes create uneven melting and can lead to sudden rolling or fragmentation as weight distribution shifts. The word iceberg comes from the Dutch word ijsberg, meaning ice mountain, this etymology reflecting the towering appearance of large icebergs that can rise tens of meters above water like floating frozen peaks. Dutch sailors exploring Arctic waters encountered these ice masses carving from Greenland glaciers, coining a term that entered English through maritime trade and exploration in polar regions. The mountain comparison proves apt for the largest icebergs, some reaching over 100 meters above sea level, heights comparable to 30-story buildings floating through the ocean, though most icebergs are considerably smaller, with exposed portions measuring 10 to 30 meters above water. The term captures ice's scale and majesty while distinguishing icebergs from sea ice, shelf ice, and other frozen water forms, creating linguistic clarity that reflects practical nautical needs to identify and describe different ice hazards encountered during polar navigation and fishing operations. Icebergs can drift for years before completely melting, surviving long journeys from polar regions toward warmer latitudes where they gradually waste away through melting, wave erosion, and fragmentation into smaller pieces. Antarctic icebergs commonly drift for 3 to 6 years before disappearing, carried by ocean currents through the Southern Ocean, occasionally reaching as far north as 40 degrees south latitude, where they encounter warm enough water to accelerate final melting. Arctic icebergs typically survive 1 to 3 years, drifting south along Labrador Current past Newfoundland, occasionally reaching as far as 40 degrees north latitude where the Titanic encountered its iceberg on an unusually southern trajectory. Drift patterns depend on ocean currents, wind, and the Coriolis effect, deflecting icebergs to the right in the northern hemisphere and left in the southern hemisphere, creating characteristic clockwise circulation around Antarctica and complex patterns in the North Atlantic where multiple currents compete to influence iceberg trajectories through cold and warm water masses. Some icebergs contain rocks and sediment from the glaciers they carved from, embedded debris that glaciers collected while flowing over bedrock, plucking fragments and incorporating them into ice that eventually carved into the ocean. When these debris-laden icebergs melt, they drop their rocky cargo onto the seafloor far from any land, creating ice-rafted debris deposits that puzzle geologists finding terrestrial rocks in deep ocean sediments. These rocks provide evidence of past ice extent and iceberg drift patterns, with rock types revealing source glaciers and deposition locations indicating historical current patterns, allowing scientists to reconstruct ice age conditions by studying sediment cores that record iceberg activity. The embedded debris also affects iceberg behavior, potentially altering melting rates, changing buoyancy if rocks concentrate in specific locations, and creating distinctive dirty bands visible in some icebergs where sediment layers mark former glacier bed positions, giving these bergs a layered appearance as internal structure becomes visible. The Titanic struck an iceberg estimated to be 50 to 100 feet above water and 400 feet below, a substantial ice mass with most of its volume hidden beneath the surface where it could damage the ship's hull despite what appeared to be adequate clearance from the visible ice. The collision occurred on April 14, 1912, in the North Atlantic where unusually southerly iceberg drift brought numerous bergs into shipping lanes, likely driven by atmospheric and oceanic conditions that pushed Arctic ice farther south than typical for that season. The impact created a series of intermittent gashes and separated hull plates along Titanic's starboard side below the waterline, damage invisible from deck but sufficient to flood multiple compartments and doom the ship despite supposedly watertight subdivisions. This disaster led to international agreements on ice patrol and ship routing, establishing monitoring systems that track icebergs and warn ships of ice dangers, significantly reducing iceberg-related maritime casualties compared to the pre-Titanic era when ice hazards received less systematic attention. Icebergs can be towed and have been proposed as freshwater sources for arid regions. This concept envisioning capturing large icebergs in the Southern Ocean and towing them to water-scarce regions where they would melt into usable freshwater. Various schemes have been proposed over decades, particularly for towing Antarctic tabular icebergs to Chile, Australia, or Middle Eastern countries, though none have yet proven economically feasible given the enormous difficulties in towing massive ice blocks across thousands of kilometers of ocean. Small-scale iceberg harvesting does occur in Newfoundland, where entrepreneurs capture small icebergs for bottled water and cocktail ice, marketing glacial ice's purity and age as premium products. While large-scale iceberg towing remains impractical with current technology, the proposals illustrate ice's value as a freshwater resource and humanity's willingness to consider ambitious engineering projects to address water scarcity, though desalination and conservation currently provide more cost-effective solutions than herding frozen mountains across oceans. Snowflakes are composed of ice crystals that form around dust particles, these microscopic nuclei providing surfaces where water vapor can deposit directly into solid ice without first condensing into liquid, a process requiring colder temperatures or higher humidity than the familiar liquid-to-solid freezing. Each snowflake begins when water vapor in sub-freezing clouds encounters a nucleating particle, dust, pollen, or other microscopic solid, and deposits onto it as ice, growing outward as additional vapor molecules add to the developing crystal. The crystal's shape depends on temperature and humidity during growth, with different conditions producing plates, columns, needles, or dendrites according to complex relationships between atmospheric conditions and ice crystal growth physics. As developing snowflakes fall through clouds, they experience varying conditions that modify their structure, creating the intricate forms we observe, each flake recording its unique path through the atmosphere in its final geometry, making snowflakes both beautiful and scientifically informative about cloud conditions. No two snowflakes are exactly alike due to countless possible crystal arrangements, this famous statement reflecting the enormous number of ways water molecules can arrange themselves into six-sided symmetric crystals during growth. While simple snowflakes like small plates or columns might occasionally duplicate, complex stellar dendrites with intricate branching patterns have such enormous configurational possibilities, roughly 10 to the 158 possible arrangements for a typical dendrite, that exact duplication becomes statistically impossible. This uniqueness arises not from fundamental laws preventing duplication but from practical reality. Each snowflake experiences a slightly different path through the atmosphere during growth, encountering unique sequences of temperature and humidity that guide development through one of countless possible trajectories. Very simple snowflakes or artificially grown crystals can match closely enough to seem identical, but natural complex snowflakes grown in chaotic atmospheric conditions reliably develop unique structures that have never existed before and will never exist again, making each flake a one-time frozen artwork. The largest snowflake aggregates on record were 15 inches wide, reported in Montana in 1887, consisting of hundreds of individual crystals that stuck together while falling through moist air, creating clumps far larger than any single crystal could grow. These aggregates formed under conditions of high humidity and temperatures near freezing, where sticky liquid coatings on crystal surfaces allowed them to adhere when colliding, gradually building massive clumps from countless smaller snowflakes. The record remains unverified by modern methods, relying on historical reports that might have exaggerated dimensions, but very large aggregates certainly occur under favorable conditions when numerous moist snowflakes bind together. Most individual snowflake crystals measure less than 1 centimeter across, with elaborate stellar dendrites rarely exceeding 5 to 6 millimeters, making these large aggregates fundamentally different from single crystals, more akin to snowballs naturally forming in midair than to single giant crystals grown from vapor. Snowflakes fall at approximately 1 to 6 feet per second depending on their size, shape and weight, with intricate stellar dendrites with high air resistance falling more slowly than compact columnar crystals or dense aggregates. This gentle descent results from the balance between gravity pulling snowflakes downward and air resistance pushing upward, creating a terminal velocity where these forces equalize and acceleration ceases. The slow falling speed, combined with atmospheric turbulence and updrafts, means snowflakes can remain aloft for extended periods, allowing them to grow larger as they accumulate additional ice through deposition and permitting them to travel considerable horizontal distances in wind before finally reaching the ground. This leisurely descent contributes to snow's effectiveness at insulating and blanketing the ground, as slowly accumulating flakes create fluffy layers with high air content that insulate better than compacted snow, making fresh snowfall an excellent thermal insulator, protecting underlying ground and plants from extreme cold. Graupel, or soft hail, forms when supercooled water droplets freeze onto falling snowflakes, coating delicate ice crystals in layers of rime ice that obscures original crystal structure and creates soft, opaque pellets. These droplets, existing as liquid water despite below freezing temperatures due to lack of nucleation sites, freeze instantly upon contact with snow crystals, building up as successive droplets collide and freeze during the snowflake's descent through cloud. The resulting graupel resembles tiny styrofoam pellets, soft enough to compress easily between fingers unlike true hail, with a granular texture from the accumulated frozen droplets. Graupel indicates vigorous atmospheric conditions with strong updrafts that support supercooled water droplets at sub-freezing altitudes, often occurring in winter storms and producing a distinctive bouncing sound when landing on surfaces, different from snow's soft accumulation or hail's harder impact, making graupel audibly identifiable to experienced observers who recognize its characteristic patter. Hail forms in thunderstorms when ice particles are repeatedly lifted and frozen, cycling through updrafts that carry them into sub-freezing cloud regions where supercooled water freezes onto their surface, adding layers with each vertical journey. This process requires powerful updrafts capable of supporting increasingly heavy hailstones against gravity, with the largest hail forming in the most intense thunderstorms where updraft speeds exceed 100 miles per hour. Each trip through the cloud adds another layer of ice, visible in cross-sections as concentric rings like tree rings, recording the number of cycles the hailstone completed before becoming too heavy for updrafts to support and finally falling to the ground. Hailstones grow from initial ice nuclei that might be frozen raindrops or graupel, accumulating mass through collision with supercooled droplets, sometimes developing complex internal structures with clear and opaque layers, reflecting different growth conditions during their turbulent formation in the violent atmosphere of severe thunderstorms. The largest hailstone recorded in the United States was 8 inches in diameter, falling in South Dakota in 2010 with a circumference of 18.62 inches and weight of nearly 2 pounds, large enough to cause serious injury or death if it struck someone directly. This monster hailstone formed in an exceptionally powerful supercell thunderstorm with extreme updrafts that could support such massive ice accumulation, cycling the stone repeatedly through freezing regions while it grew to unprecedented size. Large hail causes billions of dollars in damage annually, destroying crops, denting vehicles, breaking windows and damaging roofs, with the largest stones capable of penetrating roofing materials and falling with enough force to seriously injure livestock and people caught without shelter. The size distribution of hail in storms follows predictable patterns related to updraft strength, with stronger storms producing larger maximum hailstones, allowing meteorologists to estimate storm intensity partly through observed hail size and to issue warnings for severe hail that might threaten life and property. Cirrus clouds are composed entirely of ice crystals, these high-altitude clouds forming in the upper troposphere where temperatures remain well below freezing and water can exist only as ice, never liquid. The crystals form when water vapor deposits directly onto nuclei without passing through liquid phase, growing into various shapes including plates, columns, and rosettes depending on precise temperature and humidity conditions at cloud altitude. Cirrus clouds appear white and wispy, their delicate structure resulting from falling ice crystals creating fibrous streaks called fall streaks where crystals descend through drier air below the cloud, sometimes reaching the ground as diamond dust in cold climates. These high clouds don't produce significant precipitation at ground level because falling crystals evaporate in warmer air below, but they affect climate by reflecting some sunlight while trapping outgoing infrared radiation, creating a complex influence on Earth's radiation balance that scientists study to understand clouds' role in climate system. Ice crystals in clouds create optical phenomena like sundogs and halos, these colorful displays arising when sunlight refracts through hexagonal ice crystals oriented randomly or aligned by falling in specific orientations. Sundogs, or parhelia, appear as bright spots flanking the sun at 22 degrees to either side when plate-like crystals fall with their flat faces horizontal, refracting sunlight through their 60-degree prism faces to create these companion suns. Halos form as complete or partial rings around the sun or moon when light passes through randomly oriented crystals, the 22-degree halo being most common, though rarer halos at 46 degrees and other angles occur when light takes different paths through the crystals. These phenomena require widespread thin cirrus clouds of appropriately shaped ice crystals, often appearing during the approach of weather systems when high clouds thicken before lower clouds arrive, making sundogs and halos potential weather predictors suggesting precipitation within hours or a day. Diamond dust is a ground-level cloud of tiny ice crystals that sparkles in sunlight, forming in extremely cold, calm conditions when water vapor deposits directly into ice crystals suspended in air near the surface. This phenomenon occurs most commonly in Antarctica and the Arctic during winter, requiring temperatures typically below -30 degrees Celsius, combined with sufficient humidity and very light winds that allow delicate crystals to remain suspended rather than falling immediately. The crystals catch sunlight and create millions of tiny sparkles filling the air with glittering light, sometimes creating halos and light pillars as sunlight or moonlight interacts with the suspended ice. Diamond dust represents ice formation at its most delicate, with individual crystals measuring only microns across, so tiny they drift with the slightest air movement, transforming cold, still air into a sparkling medium that seems to materialize frozen water from nothingness, a magical effect that occurs regularly in Earth's coldest regions where conditions frequently permit this atmospheric glitter. Frost forms when water vapor deposits directly onto surfaces as ice crystals, bypassing liquid phase entirely in a process called deposition that occurs when surface temperatures drop below both the freezing point and the dew point. This direct solid-to-gas transition requires surfaces colder than the air touching them, typically occurring overnight when clear skies allow ground to radiate heat into space more efficiently than air above it, cooling surfaces below the dew point while air temperature remains slightly warmer. The resulting ice crystals grow in patterns determined by surface texture, air humidity, and temperature, creating the intricate frost designs visible on windows, grass, and other surfaces on cold mornings. Frost formation provides visible evidence of the previous night's minimum temperature and humidity conditions, with heavier frost indicating either lower temperatures or higher humidity, making frost observations useful for local weather assessment even without instruments, though frost requires different conditions than dew, which forms when surface temperatures cool below the dew point but remain above freezing. Hoarfrost creates feathery ice crystal patterns on cold surfaces, growing in delicate branching structures when prolonged sub-freezing temperatures and sufficient humidity allow extended crystal development rather than simple frost coating. These elaborate formations typically appear on fence posts, tree branches, and other exposed objects that cool efficiently through radiation on clear, calm nights when humidity remains high enough to supply continued vapor deposition. The feathery structure arises as initial ice crystals grow preferentially along certain axes according to temperature and humidity conditions, creating needles or plates that then develop secondary branches through continued vapor deposition, building intricate dendritic patterns reminiscent of snowflakes but anchored to surfaces rather than free-floating. Heavy hoarfrost can accumulate significant ice mass, weighing down power lines and tree branches enough to cause breakage, particularly when combined with wind loading, making hoarfrost both beautiful and potentially damaging, transforming winter landscapes into crystalline wonderlands while occasionally wreaking havoc on infrastructure not designed to support accumulated ice weight. Rime ice forms when supercooled fog droplets freeze on contact with objects, creating white, opaque deposits that build into the wind as droplets carried by air currents strike and instantly freeze onto exposed surfaces. This process, called riming when it occurs on falling snowflakes, creates distinctive ice accumulations on windward sides of trees, towers, and mountain summits, with ice growing into the wind as successive droplets add to the accumulation. Rime ice appears milky white rather than transparent because rapid freezing traps air bubbles between frozen droplets, creating granular structure that scatters light effectively, unlike clear ice that forms when water freezes more slowly without trapping air. Heavy rime accumulations can be spectacular, creating bizarre shapes on mountain vegetation and structures, with ice feathers extending meters into the wind, built drop by drop as fog streams past and surrenders its liquid water to any cold surface it touches, transforming familiar landscapes into alien frozen tableaus. Black ice is a thin, transparent layer of ice on roads that's nearly invisible, forming when temperature drops just below freezing allow meltwater, drizzle, or ground moisture to freeze into a smooth layer that bonds to pavement without appearing noticeably different from wet road. This hazard earns its name not from being actually black, but from its transparency that allows dark pavement to show through, making the ice effectively camouflaged until vehicles discover its presence through loss of traction. Black ice forms most commonly on bridges and overpasses that cool faster than regular roadways due to air circulation beneath them, and in shaded areas where winter sun never reaches to melt or evaporate surface moisture. The ice's smoothness provides minimal traction, surprising drivers who encounter it at normal speeds and suddenly lose steering or braking control, causing crashes that earn black ice a reputation as one of winter driving's most dangerous conditions, despite the thin ice layer being individually harmless, dangerous only through the unexpected loss of friction it creates. Fragile ice consists of fine ice crystals suspended in water, forming when turbulent rivers or ocean currents cool below freezing, creating conditions where ice nucleates throughout the water column rather than only at the surface. These needle-like crystals, typically only millimeters long, remain suspended by water turbulence despite being denser than water would suggest because their small size and irregular shapes increase drag resistance to sinking. Fragile ice gives water a milky appearance and can accumulate in enormous quantities, sometimes plugging water intakes or building up behind obstructions to create ice dams that block flow and cause flooding. In rivers, fragile ice often occurs just below waterfalls or rapids where turbulence mixes surface and deeper water, while in oceans it forms during initial sea ice formation when turbulent conditions prevent surface ice from consolidating into solid sheets, making fragile ice the first stage in sea ice development in rough waters where conventional surface freezing cannot establish stable ice. Anchor ice forms on riverbeds and lake bottoms in extremely cold conditions, growing upward from submerged rocks and vegetation when water becomes supercooled and radiative cooling from the surface or influx of extremely cold water creates sub-freezing temperatures at depth. This unusual phenomenon occurs in clear, shallow, fast-flowing streams where radiation can penetrate to the bottom and where turbulence prevents surface ice formation that would otherwise insulate deeper water. Anchor ice crystals attach to the bottom and grow upward, sometimes incorporating rocks and debris as they expand, occasionally releasing en masse to float downstream as unusual ice rafts carrying embedded bottom materials. The formation process reverses the normal expectation that ice forms at the water surface, demonstrating how specific combinations of temperature, radiation, and flow conditions can create unexpected ice behaviors, though anchor ice remains relatively rare, requiring precisely aligned conditions that occur mainly in shallow streams during the coldest winter nights with clear skies permitting maximum radiative cooling of bottom surfaces. Ice flowers form on new sea ice when water vapor crystallizes, creating delicate frost formations several centimeters tall that bloom from brine channels in young sea ice during extremely cold, calm conditions. These ephemeral structures grow when air temperatures plunge far below the ice surface temperature, creating steep temperature gradients that drive water vapor upward from unfrozen brine in the porous ice, depositing as frost in intricate crystalline patterns. Ice flowers occur primarily in the Arctic and Antarctic during initial sea ice formation, appearing in fields that transform the ice surface into gardens of crystalline blooms, though their beauty proves short-lived as wind, snow, or warming destroys these fragile structures within hours or days. The formations concentrate salt from brine channels, making ice flowers exceptionally salty, and they provide habitat for specialized bacteria and algae that colonize these transient microenvironments, creating unexpected biological activity in one of Earth's most inhospitable settings, demonstrating life's ability to exploit even the most fleeting and extreme conditions. Frost flowers can be several centimeters tall with delicate crystal structures. These vertical ice formations growing through sustained vapor deposition under very cold conditions where continued crystal development builds elaborate branching patterns. The tallest frost flowers, which can reach 4 to 5 centimeters, develop during extended periods of extreme cold combined with steady vapor supply, allowing crystals to expand upward over hours rather than quickly completing their growth. Each flower's structure reflects the precise temperature and humidity history during its growth, with different conditions producing different crystal habits, needles, plates, or complex branching forms, making frost flowers readable records of atmospheric conditions, though few people possess the knowledge to interpret their crystalline language. These formations remain fragile, easily destroyed by wind or touch, existing only in protected locations where calm conditions permit delicate crystal architecture to develop without mechanical disruption, making intact frost flowers indicators not just of cold temperatures but also of calm conditions allowing their survival. Needle ice forms in soil when water freezes and pushes up columns of ice, this formation occurring in exposed soil during nights when surface temperature drops below freezing while deeper soil remains above freezing, creating conditions where water migrates upward and freezes at the surface. The needles grow perpendicular to the surface as continued freezing at the soil-air interface draws more water upward through capillary action, the accumulating ice lifting attached soil particles and creating fragile columns that can reach several centimeters in height. This process, called frost heaving, can disrupt plant roots and disturb soil structure, affecting agriculture and ecosystems in regions experiencing freeze-thaw cycles. Needle ice typically melts quickly after sunrise, leaving behind characteristic disturbed soil patterns, though repeated freeze-thaw cycles can substantially modify soil texture and distribution over winter months, gradually moving soil particles downslope through incremental shifts each time needle ice forms and then collapses, a slow but persistent form of erosion driven by water's expansion when freezing. Candle ice forms vertical columns as lake and sea ice begins to melt in spring, the ice structure decomposing into separate columnar crystals that separate from each other while remaining vertically oriented, creating ice that resembles a bundle of frozen candlesticks. This structure develops because ice crystals in freezing water grow preferentially downward with their C-axis horizontal, creating vertically oriented grains, and when melting begins, grain boundaries melt preferentially, allowing individual crystals to separate. The resulting candle ice becomes weak and hazardous despite appearing solid, capable of supporting weight in one direction, while offering minimal resistance to forces separating the columns, making late-season ice treacherous for travel as surface appearance no longer indicates structural integrity. The formation signals spring's arrival and ice's imminent breakup, with candle ice typically existing only briefly before final melting or mechanical breakup scatters the columns, making this crystal structure one of ice's final forms before reverting to liquid water at season's end. Mars has polar ice caps composed of water ice and frozen carbon dioxide, these layered deposits waxing and waning seasonally as carbon dioxide sublimates in summer and deposits in winter, while water ice remains mostly stable year-round. The southern cap appears almost entirely carbon dioxide ice with some water ice at depth, while the northern cap is predominantly water ice overlain by seasonal carbon dioxide frost that appears each winter and sublimates each summer. These caps reach several kilometers thick in places, containing layered deposits that record Martian climate history analogously to ice cores on Earth, with layer characteristics revealing information about past atmospheric conditions, dust deposition and climate cycles. The cap's permanent portions represent significant reservoirs of volatiles on Mars, and their behavior affects atmospheric pressure noticeably as seasonal carbon dioxide sublimation and deposition transfers substantial mass between cap and atmosphere, creating measurable changes in surface pressure as carbon dioxide cycles between solid and gaseous phases with the changing seasons on this frozen desert world. Europa, Jupiter's moon, has an icy surface covering a possible liquid ocean, this ice shell ranging from perhaps 15 to 25 kilometers thick according to various estimates, floating atop a global ocean that might contain more water than all of Earth's oceans combined. The surface ice displays remarkable features: long linear cracks, chaotic terrain where ice appears broken and refrozen, and relatively few impact craters suggesting a young surface that's been recently resurfaced through geological activity. This activity likely results from tidal heating as Jupiter's gravity flexes Europa's interior during its elliptical orbit, generating enough heat to maintain liquid water beneath the ice despite Europa's extreme distance from the Sun. Scientists consider Europa one of the solar system's most promising locations for life beyond Earth, with its subsurface ocean potentially providing the liquid water, chemical nutrients and energy sources that life requires, making this icy moon a prime target for future exploration missions designed to probe through the ice to the hidden ocean below. Enceladus, Saturn's moon, shoots geysers of ice particles into space, these dramatic plumes erupting from cracks near the South Pole called tiger stripes, ejecting water vapor and ice grains that feed Saturn's E-ring with fresh material. The geysers indicate liquid water exists beneath Enceladus's icy surface, warmed by tidal heating from Saturn's gravity similar to Europa, but on a smaller moon where such activity seems surprising given Enceladus's modest size of just 500 kilometers diameter. The ejected material includes organic molecules and salts that suggest the subsurface ocean contacts a rocky core, creating chemical interactions that could potentially support life, making tiny Enceladus another compelling target for astrobiology despite its remote location and small size. The geysers vary in intensity, correlating with Enceladus's orbital position, suggesting that tidal forces modulate their activity, opening and closing fissures that allow pressurized ocean water to escape as the moon flexes during its elliptical orbit around Saturn. Comets are often called dirty snowballs due to their ice and dust composition. These primitive solar system objects consisting of frozen water, carbon dioxide, methane and ammonia mixed with rocky dust and organic compounds left over from the solar system's formation. When comets approach the Sun, solar heating sublimes surface ice into gas that escapes into space carrying dust particles, creating the characteristic coma and tail that make comets visible from Earth despite their small nucleus size typically measuring only a few kilometers across. The ice preserves pristine material from the early solar system, relatively unchanged over 4.6 billion years because comets spent most of their existence in the cold outer solar system where minimal heating allowed ice to remain frozen, making comets valuable scientific targets that might reveal conditions during the solar system's birth. Recent spacecraft visits to comets revealed surfaces more complex than simple dirty snowballs, with varied terrain features, active and inactive regions, and layered structures suggesting complex formation histories, though the basic description of ice and dust composition remains fundamentally accurate. Pluto's surface is covered in nitrogen, methane, and water ice, this distant world displaying a surprising diversity of frozen materials despite its extreme cold and distance from the Sun at 40 times Earth's distance. Nitrogen ice dominates the bright heart-shaped plain called Sputnik planitia, slowly flowing in convective cells despite frigid temperatures around -230 degrees Celsius because nitrogen ice remains relatively soft even at these extremes. Water ice, as hard as rock at these temperatures, forms Pluto's mountains and basement rock, while methane ice appears on highlands and pole regions, subliming into the thin atmosphere during warmer parts of Pluto's 248-year orbit around the Sun. The surface displays remarkable complexity that shocked scientists when New Horizons spacecraft returned detailed images in 2015, revealing a geologically active world with flowing glaciers, possible ice volcanoes, and varied terrain features despite being a frozen ball 5 billion kilometers from Earth, demonstrating that interesting geology isn't limited to warm worlds near the Sun. Saturn's rings are composed primarily of water ice particles. These spectacular bands containing chunks ranging from dust-sized grains to house-sized boulders, all orbiting Saturn in a thin disk barely 10 meters thick despite extending over 400,000 kilometers in diameter. The particles are nearly pure water ice, reflecting light efficiently and giving the rings their bright appearance, though some rings contain more dust or have slight color variations suggesting minor contamination with other materials. The origin of Saturn's rings remains debated, with theories ranging from primordial material left over from Saturn's formation to the relatively recent breakup of a moon destroyed by tidal forces or impact. Whatever their origin, the rings prove dynamically complex, with gravitational interactions between particles and Saturn's moons creating gaps, waves, and intricate structure within what appears from distance to be smooth bands, making Saturn's rings a natural laboratory for studying planetary disk dynamics applicable to understanding debris disks around distant stars and the protoplanetary disks where planets form. The ice on Mars's polar caps contains layered deposits revealing climate history, these alternating layers of ice and dust recording variations in Mars's orbital parameters and resulting climate changes over millions of years. The layers, visible in cross-section where erosion has exposed them, show dark, dust-rich bands alternating with brighter ice-rich layers, analogous to tree rings recording growth conditions or Earth's ice cores recording atmospheric history. Scientists interpret the layering as resulting from variations in Mars's axial tilt and orbital eccentricity that cycle on timescales of hundreds of thousands of years, affecting how much solar radiation reaches polar regions and thus controlling ice accumulation and dust deposition rates. By counting and measuring layers, planetary scientists reconstruct several million years of Martian climate history, revealing a complex pattern of ice ages and warmer periods, though all occurring within what Earth would consider extreme cold, showing that even frigid Mars experiences climate variations driven by orbital mechanics similar to the Milankovitch cycles that pace ice ages on Earth. Titan, Saturn's largest moon, has lakes of liquid methane but also water ice bedrock. This fascinating world maintaining stable liquid on its surface, not through water's persistence as on Earth, but through methane and ethane remaining liquid at Titan's frigid -179 degrees Celsius surface temperature. Water ice, frozen solid as rock at these temperatures, forms Titan's crust and mountains, eroded by methane rain that carves river valleys and lake basins in this rock-hard ice exactly as water erodes silicate rock on Earth. The methane cycle on Titan parallels Earth's water cycle, with liquid evaporating from lakes, forming clouds, precipitating as rain, and flowing in rivers back to lakes, creating familiar hydrological processes but operating with exotic fluids at temperatures where water would be hard as granite. This unique environment makes Titan relevant for astrobiology despite extreme cold, as it demonstrates that liquid-based chemistry can operate with substances other than water, potentially supporting life forms based on different biochemistry adapted to drastically different conditions than anything found on Earth. Some asteroids contain significant amounts of water ice, particularly those in the outer asteroid belt and Jupiter's Trojan populations, where solar heating remains minimal and ice can persist on or near surfaces without rapid sublimation. Detection comes from spectroscopic observations, revealing water ice absorption features, and from measurements of density too low to be explained by rock alone, requiring significant ice content to match observed values. This ice proves important for understanding solar system formation and evolution, showing where water existed in the early solar system and potentially providing clues about how Earth acquired its water during planet formation. The ice also has practical implications for future space exploration, as water-rich asteroids could serve as refueling stations for spacecraft, with ice processed into rocket fuel and life support consumables, making asteroids both scientifically interesting relics of solar system formation and potentially valuable resources for expanding human presence beyond Earth. Mercury, despite being closest to the Sun, has water ice in permanently shadowed craters. These deposits surviving in polar regions where crater rims cast permanent shadows into deep basins that never receive direct sunlight. Temperatures in these shadowed regions plunge below -170 degrees Celsius, despite Mercury's proximity to the Sun, cold enough to preserve ice for billions of years without significant sublimation, making these craters effective cold traps accumulating and preserving water delivered by comet impacts or solar wind interactions over Mercury's history. Radar observations from Earth detected highly reflective material consistent with water ice, and NASA's Messenger spacecraft confirmed the deposits through multiple lines of evidence, including neutron spectroscopy that detected hydrogen consistent with water ice. This counterintuitive presence of ice on the solar system's hottest planet demonstrates that temperature depends on local conditions rather than just distance from the Sun, with permanent shadow creating pockets of extreme cold even on a world where sunlit surfaces reach 430 degrees Celsius, hot enough to melt lead. Ancient Persians built ice houses called yakhchans to store ice year-round. These ingenious structures using passive cooling through evaporation, radiation, and wind-catching architecture to maintain sub-freezing temperatures even during hot desert summers. The buildings featured thick insulated walls, often 2 meters thick, constructed from water-resistant mortar called saruj that insulated effectively while preventing moisture penetration. Underground storage chambers connected to wind catchers that channeled cool breezes through the structure, and shallow pools that froze during winter nights provided the ice that yakhchans preserved for months. These ancient refrigerators, some still standing after hundreds of years, demonstrate sophisticated understanding of heat transfer and architectural climate control, allowing ice harvested from winter's cold to survive summer's heat through purely passive engineering. The tradition of ice storage spans millennia in Persia, with some yakhchans providing ice well into the 20th century before electric refrigeration made them obsolete, though many remain as historical monuments to pre-industrial cooling technology. The ice trade in the 1800s shipped ice from frozen lakes to tropical regions, creating an industry that exported winter's cold across oceans and continents before mechanical refrigeration made natural ice obsolete. The trade began in New England, where entrepreneurs realized that ice cut from frozen ponds could be profitably shipped to warm climates if properly insulated during transport with sawdust that prevented melting on voyages lasting weeks or months. Ships carried ice from Massachusetts to the Caribbean, South America, India, and even Australia, with enough ice surviving the journey to generate substantial profits despite significant melting losses. The trade required carefully timed operations, cutting ice in winter, storing it in insulated ice houses, and shipping it during sailing seasons that balanced ice preservation against delivery schedules. This remarkable commerce existed for roughly a century until artificial ice production in the 1890s gradually eliminated demand for natural ice, though the trade's peak saw hundreds of thousands of tons of ice harvested annually and shipped worldwide, a pre-industrial global cold chain. Frederick Tudor became known as the Ice King for pioneering the commercial ice trade, building a business empire based on harvesting ice from Massachusetts ponds and shipping it to tropical ports where cold commanded premium prices. Tudor began in 1806 with an audacious plan to sell New England ice in the Caribbean, initially losing money as inefficient handling resulted in excessive melting and skeptical customers weren't yet convinced of ice's value. Through persistence and innovation, improved insulation methods, more efficient harvesting tools, and marketing that created demand for previously unknown products like iced drinks, Tudor eventually established a profitable enterprise that made his fortune and earned his royal nickname. His success required not just solving technical problems of ice preservation, but also creating markets where none existed, convincing tropical populations that ice represented not a luxury curiosity, but a valuable commodity worth paying for, demonstrating how entrepreneurial vision could identify and develop entirely new commercial opportunities. Ice harvesting was a major industry before mechanical refrigeration, employing thousands of workers who cut ice from frozen lakes and ponds during winter, using specialized tools including ice saws, chisels, and tongs to efficiently extract large blocks. The work proceeded in assembly line fashion. Workers scored the ice surface into grid patterns, sawed along the lines to separate blocks, then used ice tongs to remove blocks and slide them up ramps onto wagons or into storage buildings. The industry peaked in the late 1800s when hundreds of ice companies operated across North America and Europe, harvesting millions of tons annually from natural ice fields maintained through careful management. Ice houses, insulated buildings that stored cut ice until needed, dotted landscapes near major cities, while railroads developed specialized insulated cars for ice transport to distant markets. This labor-intensive industry provided winter employment in agricultural regions but gradually disappeared as ammonia compression and other mechanical refrigeration technologies made artificial ice production more economical than natural ice harvesting, completely transforming food preservation and climate control within a few decades. The first artificial ice rink opened in London in 1876, using a mixture of glycerin and water with ether, nitrogen and carbon dioxide to create and maintain ice mechanically rather than depending on natural winter cold. This innovation, called the glaciarium, represented a breakthrough that allowed ice skating year-round in any climate, liberating the sport from seasonal and geographic limitations. The technology evolved rapidly as ammonia compression systems replaced earlier chemical cooling methods, becoming more reliable and economical, enabling proliferation of artificial rinks that made ice sports accessible to far more people than natural ice ever could. These early rinks paved the way for modern ice hockey's development as a standardized sport played indoors on consistent ice surfaces and enabled figure skating to develop its technical difficulty beyond what outdoor ice's variable conditions permitted. The artificial rink revolution transformed ice sports from seasonal outdoor activities to year-round indoor sports with controlled conditions, dramatically expanding participation and enabling the development of ice sports into the professional international activities they've become. Ice hotels are built entirely from ice and snow, rebuilt each winter as architectural artworks that melt away each spring only to be recreated in different designs when winter cold returns, making each season's hotel unique. These structures use massive blocks of clear ice harvested from rivers for walls, columns, and even furniture, while snow provides insulation and creates domed ceilings that support themselves through proper geometry. Inside, temperatures hover around -5 degrees Celsius to -8 degrees Celsius, cold enough to prevent melting but not uncomfortably frigid for guests sleeping in specialized thermal sleeping bags on beds made from ice blocks covered with reindeer hides. The hotels feature ice sculptures, frozen art installations, and ice bars serving drinks in glasses carved from ice, creating immersive frozen environments that attract tourists willing to pay premium prices for a night in unique accommodations. The concept originated in Sweden in 1989 and has spread globally, with similar ice hotels now operating in Norway, Finland, Canada, and Romania, each offering temporary frozen architecture that showcases ice's structural and artistic possibilities while celebrating winter's creative potential. The Ice Palace in St. Paul, Minnesota has been built intermittently since 1886, celebrating the city's winter climate with massive frozen castles constructed from blocks cut from local lakes and assembled into architectural marvels. The tradition began after a New York journalist mockingly called St. Paul another Siberia, unfit for human habitation, prompting locals to embrace their winter identity by constructing an ice palace and hosting a winter carnival demonstrating that cold didn't diminish their city's vitality. The palaces, when built, tower several stories high, featuring walls, towers, turrets, and battlements constructed entirely from clear ice blocks that create translucent structures visible from across the city. Not every year produces sufficient ice or funding to build a palace, making successful builds special occasions that draw hundreds of thousands of visitors to winter festivals featuring parades, ice sculpture competitions, and celebrations of northern winter culture. The tradition represents defiant pride in cold climate, transforming potential liability into celebrated identity, showing how communities can embrace rather than merely endure their environmental conditions. Indigenous peoples have used ice for food preservation for thousands of years, particularly in Arctic and subarctic regions where natural freezing provides reliable year-round refrigeration that preserves meat, fish, and other perishables without technological intervention. The practice involves digging storage cellars into permafrost that maintain sub-freezing temperatures perpetually, creating natural freezers that reliably preserve food supplies through seasons when hunting and gathering might prove difficult or impossible. Some communities also cache food underwater in ice-covered lakes where cold temperatures combine with limited oxygen to prevent spoilage, or bury food in snowbanks during winter when above-ground temperatures ensure frozen storage. These traditional practices demonstrate sophisticated understanding of ice's preservative properties developed through millennia of Arctic living, knowledge enabling human survival in environments where agriculture remains impossible and hunting success varies seasonally, making reliable food storage essential for bridging gaps between abundance and scarcity. Modern technology has largely replaced these traditional methods, even in Arctic communities, though knowledge persists as cultural heritage even where electric freezers have become standard. Ice sculpting competitions showcase ice's workability when near freezing, artists using chainsaws, chisels, and specialized tools to carve elaborate sculptures from clear ice blocks weighing hundreds of kilograms, creating detailed artworks ranging from realistic figures to abstract designs. The medium's challenges include ice's brittleness that makes it crack unexpectedly, its transparency that requires different compositional thinking than opaque materials, and its temporary nature as warming eventually melts even indoor sculptures despite refrigeration. Competitions typically impose time limits, requiring sculptors to work quickly and decisively, planning their approach carefully because removed material cannot be reattached and mistakes cannot easily be corrected. The sculptures shine most dramatically when backlit, allowing light to pass through clear ice while highlighting carved textures and details, creating luminous effects impossible with opaque materials. Major competitions attract sculptors worldwide, with events in Fairbanks, Alaska, Harbin, China, and other cold climate cities showcasing artistic skill while celebrating winter's creative possibilities, demonstrating that ice serves not just as physical necessity, but also as aesthetic medium offering unique artistic opportunities. The Harbin Ice Festival in China features massive ice structures with colored lights, this annual event creating a temporary city of frozen architecture built from blocks harvested from the nearby Songhua River and carved into buildings, pavilions, and sculptures up to 50 meters tall. Construction teams work for weeks cutting thousands of cubic meters of ice, transporting blocks to the festival site, and assembling them into elaborate structures that cover over 800,000 square meters. LED lights embedded within the ice illuminate structures from within, creating brilliant colored displays visible across distances, transforming nighttime visits into walks through glowing frozen landscapes. The festival, running from late December through February, attracts millions of visitors annually despite average winter temperatures around -17 degrees Celsius, demonstrating ice's appeal as both engineering material and artistic medium. The event showcases Chinese ice carving traditions while competing for recognition as the world's largest ice and snow festival, with scale and ambition that transforms winter from potential hardship into celebrated spectacle, embodying the philosophy of embracing rather than merely enduring cold season. Ice skating works primarily due to ice's quasi-liquid surface layer, a permanent microscopic layer of slippery, disordered water molecules that exists even without pressure or friction, making ice inherently slick even before skaters apply forces. This surface layer, typically only nanometers thick, consists of water molecules that can't bind properly into the crystalline lattice at the air-ice interface, remaining in a partially liquid state that provides lubrication. While pressure from skate blades and friction from sliding do generate additional melting that enhances lubrication, modern research confirms the quasi-liquid layer as the primary reason for ice's low friction, existing even at extremely cold temperatures and explaining why ice remains slippery regardless of temperature or skating speed. This permanent liquid film distinguishes ice from most solids, making frozen water uniquely suited for sliding sports, and explaining why skating is possible even at Antarctic temperatures of -40 degrees Celsius, where pressure melting and friction would be insufficient alone to create the liquid layer necessary for smooth gliding. The Mpemba effect describes how hot water can freeze faster than cold water under certain conditions, a counterintuitive phenomenon named after a Tanzanian student who noticed it while making ice cream and questioned his teachers about the observation. The effect doesn't occur universally but requires specific conditions, particular starting temperatures, container geometry that affects convection patterns, and cooling environments that favor certain heat transfer mechanisms. Several mechanisms potentially contribute, including more efficient evaporation from hot water reducing the mass that needs freezing, different convection patterns that affect heat transfer, or supercooling behavior differences between samples. Despite its discovery dating back to Aristotle and modern rediscovery by Mpemba in the 1960s, scientists still debate the effect's precise mechanisms and conditions that reliably produce it, making it a fascinating example of how everyday phenomena can harbor complex physics not yet fully understood, despite seeming simplicity. Supercooled water can remain liquid below 0 degrees Celsius until disturbed, existing in a metastable state where it should freeze but lacks the nucleation sites or disturbance necessary to trigger crystallization. Pure water in clean containers can supercool to -40 degrees Celsius or below before finally freezing spontaneously, remaining liquid far below its equilibrium freezing point, because forming ice requires initial crystal nuclei and molecules rarely spontaneously organize into the ordered structure without seeds or perturbations. Even gentle vibration, introduction of ice crystals, or addition of nucleating particles can trigger instant freezing as supercooled water rapidly crystallizes once nucleation begins, releasing stored latent heat and warming toward 0 degrees Celsius as it solidifies. This behavior affects weather, with supercooled cloud droplets remaining liquid at sub-freezing altitudes until colliding with ice crystals or aircraft that trigger sudden freezing, creating icing hazards for aviation and contributing to precipitation formation through processes involving both supercooled water and ice crystals coexisting in clouds. Ice has a relatively high latent heat of fusion at 334 joules per gram, meaning substantial energy must be added to melt ice even after it reaches 0 degrees Celsius, with this energy going into breaking hydrogen bonds rather than increasing temperature. This high heat capacity makes ice effective for cooling, as melting ice absorbs significant thermal energy from its surroundings while maintaining constant temperature, explaining why ice-water mixtures reliably maintain 0 degrees Celsius until all ice melts. The same property works in reverse during freezing, with crystallizing water releasing large amounts of heat, moderating temperature drops, and explaining why bodies of water resist freezing until substantial heat extraction has occurred. This thermal property affects climate, with sea ice formation releasing heat that warms overlying atmosphere while melting absorbs heat that cools surroundings, creating feedback effects that influence polar weather patterns and making phase transitions between ice and water significant factors in Earth's heat budget and climate system. Regelation allows ice to refreeze after pressure is removed, this process enabling phenomena like ice skating's self-healing of grooves cut by blades, and glaciers flowing around obstacles then refreezing on the downstream side. The process works because increased pressure temporarily lowers ice's melting point, creating liquid water at pressure points that refreezes when pressure is removed and temperature returns above the depressed melting point. Classic demonstrations show weighted wires cutting slowly through ice blocks while the block remains intact because water squeezed out by wire pressure refreezes above the wire, allowing the wire to pass through while ice repairs behind it. However, regulation's importance in skating and glaciology is less than historically believed, with the quasi-liquid surface layer and ice deformation now recognized as more significant for these phenomena. Nevertheless, regulation does occur and contributes to ice's unique mechanical properties, allowing it to flow and deform in ways impossible for most crystalline solids, helping explain glacial ice's ability to move as a coherent mass despite being brittle solid. Ice's thermal conductivity is about 4 times that of water, allowing heat to transfer through solid ice more efficiently than through liquid water, though both remain poor conductors compared to most solids. This property means that ice conducts warmth from warmer to colder regions within the ice structure, while water's lower conductivity creates greater temperature stratification in liquid. The difference affects freezing rates, with ice's higher conductivity allowing heat to escape more readily from the freezing front, but also means ice layers provide better thermal connection than equivalent water layers. In practical terms, ice's thermal conductivity remains low enough that thick ice effectively insulates water beneath from extreme air temperatures above, protecting aquatic ecosystems, while being high enough that ice temperature throughout a frozen layer equilibrates relatively quickly compared to water's tendency to maintain stable temperature layering for extended periods. The triple point of water where ice, liquid and vapor coexist is 0.01 degrees Celsius at 611.657 pascals, this specific combination of temperature and pressure being the only condition where all three phases can exist simultaneously in equilibrium. Below the triple point pressure, ice sublimates directly to vapor without melting through a liquid phase, while above it, normal melting and evaporation occur through liquid intermediary. The triple point serves as a fundamental reference for temperature scales, with the Kelvin defined such that water's triple point equals exactly 273.16 Kelvin, making this unique phase transition point a calibration standard for precision thermometry. The low pressure required, less than 1% of atmospheric pressure, explains why the triple point rarely occurs naturally on Earth's surface where pressure typically exceeds this value, though it can be observed in laboratory conditions or potentially on Mars where atmospheric pressure occasionally approaches the triple point value, allowing brief appearances of liquid water despite generally sub-freezing temperatures. Ice's surface is covered by a quasi-liquid layer even below freezing. This molecular scale region of disorder existing permanently at the ice-air interface where water molecules cannot properly integrate into the crystalline lattice, creating a film resembling liquid water in its molecular mobility and lack of structure. The layer's thickness depends on temperature, growing thicker as temperature approaches the melting point and thinning at colder temperatures, but never disappearing entirely even at extreme cold. This permanent liquid-like film provides the primary lubrication that makes ice slippery, affecting everything from skating to glacier sliding to ice's adhesive properties and electrical characteristics. Scientists discovered this layer relatively recently, despite ice's familiarity, demonstrating how even common substances can harbor unexpected properties requiring sophisticated experimental techniques to detect and characterize, and showing how surface properties can differ dramatically from bulk behavior even in simple materials like frozen water. Researchers study ice nucleation to understand cloud formation and precipitation, investigating how water vapor or supercooled droplets transition to ice in atmospheric conditions, a process crucial for weather and climate but still incompletely understood. Ice nucleation requires nucleating particles, dust, bacteria or other aerosols, that provide surfaces where water molecules can arrange into ice crystal structures, with different particles varying dramatically in their effectiveness. Understanding which particles nucleate ice efficiently and under what conditions helps explain cloud properties, precipitation formation, and climate effects. Since ice in clouds affects how they reflect sunlight, emit infrared radiation, and produce precipitation. This research combines laboratory experiments freezing water on various surfaces, atmospheric measurements detecting ice nucleating particles, and theoretical studies of molecular scale processes, gradually revealing the complex factors controlling when and where ice forms in clouds, knowledge essential for improving weather forecasting and climate modeling where cloud processes remain among the largest uncertainties. Climate scientists monitor ice extent and thickness as key indicators of global warming, measuring these properties through satellite observations, field surveys, and automated monitoring stations that track changes in glaciers, ice sheets, sea ice, and permafrost worldwide. Ice responds sensitively to temperature changes, expanding in cold and contracting in warmth, making its extent and volume reliable indicators of climate trends integrating temperature variations over time. Observations show widespread ice retreat, glaciers shrinking globally, Arctic sea ice declining in extent and thickness, ice sheets losing mass to ocean, and permafrost warming and thawing at increasing rates. These changes represent not just abstract metrics, but real consequences affecting sea level, polar ecosystems, indigenous communities, and global climate feedbacks where ice loss amplifies warming by exposing darker surfaces that absorb more sunlight. The monitoring effort combines ground-based measurements, aircraft surveys, and satellite observations into comprehensive datasets revealing ice's response to changing climate, providing crucial evidence of warming's reality and measuring one of its most visible and consequential impacts on Earth's physical geography. And so we complete our journey through 100 facts about ice, this remarkable substance that shapes landscapes, preserves history in frozen layers, and exists throughout our solar system in forms both familiar and exotic. Ice connects Earth's coldest regions with distant moons, links molecular forces to planetary processes, and transforms winter into a season of crystalline beauty rather than mere hardship. As you drift towards sleep, let these truths about frozen water accompany you gently, reminding you that ice has preserved mammoth carcasses for millennia, carved valleys through patient grinding, and floats because of a fortunate quirk of chemistry that makes solid less dense than liquid. Rest well, knowing that ice continues its work across our world and beyond, freezing, melting, flowing, and crystallizing in endless cycles that connect water's three phases through transformations both ordinary and profound.